Okay, thanks. I'll talk a little bit at the end about axion electrodynamics, but and about so it's a little bit out of order with respect to the previous talk, but I'll come at it from a different perspective. So basically, what I wanted to talk about today is Wannier functions and using Wannier functions as a basis, which is a tight binding-like basis, but based on first principles calculations through a technique called Wannier interpolation, which is used very commonly nowadays when going from first principles calculations to topological properties or, in some cases, towards transport properties and so on. So I thought it would be useful to introduce all of this. And it's also related to electric polarization, which is a topic that is not particularly relevant to the current school, but is central to the understanding of some things and topological properties. So I thought we should include that as well. And then at the end, I'll talk about orbital magnetoelectric coupling insofar as I have time, and about axion electrodynamics. So the axion angle, what is the axion angle, and then how does that enter into equations of motion? So let me start for Wannier functions, and to start here, I start at the chemical level. So here's a trivial, so start simple, right? Two hydrogen atoms forming a hydrogen molecule. They each have one electron. The electrons both go into a bonding state, and the antibonding state is empty. And so there's really, discounting spin, only one occupied state. There's not much you can do. But if you have two helium atoms that you artificially bring together somehow, then the electrons occupy both the bonding state and the antibonding state. And from first-year quantum mechanics, you'll describe this in terms of two eigenstates, the occupied state and the unoccupied, I'm sorry, they're both occupied state, the lower energy and the higher energy state. But that's not the only way of representing the occupied subspace. And in fact, it's the occupied subspace rather than the individual levels that come into many properties. For example, the expectation value of single particle operators traced over the occupied space. And so rather than using the bonding and antibonding combinations that appear naturally in the solution of the Schrodinger equation, you can re-separate these by taking even and odd linear combinations and construct what are called localized molecular orbitals. This one is mostly localized on the first hydrogen atom, and this one is mostly localized on the second hydrogen atom. So LMO stands for localized molecular orbitals, and this is a concept that goes back in chemistry for many decades. Boy's localization, if you have encountered that term. And so the idea is this: suppose for a molecule, you take all of your occupied states, those are the psi n, where n runs over the number of occupied levels, and you carry out some unitary transformation among those that generates some other set of states, phi j, that are as localized as possible. Then these phi j, since this is a unitary transformation, these phi j, while not being eigenstates anymore, the set of phi j will span exactly the same space as the set of psi n. And if you build a Slater determinant out of the psi j, it's actually the same thing as the Slater determinant built out of psi n. And so they describe everything in exactly the same way. I'm in a single particle framework here. And there were several criteria that were proposed for what you want to mean by the maximally localized orbital. The one that I will focus on and that was generalized to the crystal context is the Boy's criterion, which is basically minimizing the variance of each of these localized molecular orbitals in real space. So this variance really means that you minimize, for each localized molecular orbital, you find its center, and then you minimize the spread around the center. So it's a minimized quadratic spread approach. There are iterative procedures that you use to implement and minimize these things, and you generate these localized molecular orbitals. And then for some computational chemistry applications, and to some degree for chemical intuition, they tell you, they provide useful a basis for example, you may only need to include interactions between nearby localized molecular orbitals in a large molecule, and that greatly simplifies the description. So in the 90s, we came across the question of how to generalize this to crystalline systems, and the problem is that a matrix element like this between two molecular orbitals is easy to compute because molecular orbitals decay exponentially outside the molecule, and the fact that R blows up indefinitely when you get to large position doesn't cause a problem. But if you try to evaluate matrix elements of the X or the X squared operator or Y squared in a crystalline system, you have a problem because the block functions go to infinity and these operators blow up. And so the initial paper by Marzari and myself was in 1997, where we suggested a mechanism, we suggested a procedure for implementing the Boy's minimal spread criterion in a crystalline solid. And here I give you several references, and I highlighted in green the ones that I would recommend going to first. This one is a Reviews of Modern Physics, about a decade old, which is the framework of Wannier functions, which are the localized molecular orbitals in the crystalline environment, are called Wannier functions. And there's also a code, a post-processing code named Wannier 90, which you run after a conventional DFT, a density functional first principles calculation, that is used to generate the Wannier functions and a Wannier representation of the band structure. And this code is now very widely used in the topological community. And so it may show up, for example, in the hands-on workshop that happens later in the week. Okay, so the basic approach is illustrated here, and let me try to go through this. So here we're in a crystal. Let's say we're in the silicon crystal. We're interested in 4 occupied valence bands. So N runs from 1 to 4, and K runs over the 3-dimensional Brillouin zone. And what you want to do is construct eventually some localized Wannier functions. These Wn are localized Wannier functions. So if there are 4 occupied bands, you're going to want to have 4 Wannier functions in the unit cell. And those Wannier functions, plus all of their periodic images, are going to span exactly the same Hilbert space, subspace, as is spanned by all the block functions, so that you can use these Wannier functions. Even though they're not eigenstates anymore, you can use them to represent the occupied subspace in the same way. And you can also use them as a tight binding model, as I'll show you later on. Okay, so what you have to do, so what I said here is that there's some unitary matrix that mixes these things. In the case of a molecule, there's just a finite number of them. It turns out that in the crystal, when you work at a given wave vector k, this is again just a 4x4 matrix, but now it depends upon wave vector k. And so what you have to do is you have to choose a unitary 4x4 matrix, not just once, but as a function of k. And here's the trick. The trick is that you take these block functions and you construct these unitary matrices in such a way that you get what I'll call over here are pseudo-block functions. These pseudo-block functions are not eigenstates of the Hamiltonian anymore, but they have block-like character. In other words, when you translate by a lattice vector, you get the same phase, e to the I k dot r, that you got from the original ones. So we'll call these pseudo-block functions, and they're normalized because that u is unitary. And you want these to be as smooth as possible in k. And the basic idea, as you probably know from Fourier transformations, is if something is smooth in reciprocal space, then it looks localized in real space and vice versa. And so we want something that's as localized as possible in real space. So you choose these unitary matrices to make these as smooth as possible in reciprocal space. Then you do the Fourier transform to construct the Wannier functions from the block functions. And so the Fourier transform of a smooth function makes localized functions. So let me explain the notation here. The Wannier function, there's a set of Wannier functions that are labeled by R, which is identifying the unit cell, and n, which runs over the 4 Wannier functions in the unit cell. And so the first subscript tells you which cell this Wannier function is localized in, and n tells you the band-like index. They don't correspond one-to-one by bands because these unitary matrices mix up the different bands. So once you've done that, you've got these localized Wannier functions. Actually, they have the periodicity property that the one in this unit cell is just the translation of the one in that unit cell. So the information that you need to record really is just what are all the Wannier functions in the home unit cell. That's what the 0 means. And then there's an iterative procedure in which you adjust these unitary matrices further in such a way as to minimize this spread, which is equivalent to saying that I want psi tilde to be as smooth as possible. And when you do that, so let me explain a little bit again how you go from block functions to Wannier functions. So the basic idea that we have talked about before is that each block function is some underlying cell periodic wave function times a phase factor. And so if you take a linear combination of block states with different wave vectors k, you can make something that looks like a wave packet in real space, and we're trying to make the most localized possible wave packet. To do that, you want to use as much of reciprocal space as you can, and you have the whole Brillouin zone, so you use the whole Brillouin zone, which is basically what we're doing here. We're making a wave packet by integrating over the whole Brillouin zone. We want something as localized as possible, so it has to be as delocalized as possible in reciprocal space, so you integrate over the whole Brillouin zone. So here's an example, sort of a one-dimensional cartoon. You have some single unit cell of a periodic crystal, and here's the one-dimensional Brillouin zone in the x direction. And if I discretize the Brillouin zone with 6 k points in the mesh of reciprocal lattice vectors of the wave vector index k and construct those 6 block states, each one of the block states extends throughout this supercell of 6 primitive cells. And so, for example, that block state looks something like what I drew here. And if I take a sum of all of those 6 block states, I end up with something which is as localized as possible. Here I'm assuming that I've made the choice of phases if there is a problem in such a way that the evolution is as smooth as possible. Then I get a Wannier function in the home unit cell. That's this formula. If I insert a phase factor, e to the ik dot r, inserting the phase factor in reciprocal space is like doing a translation in real space, so I get this Wannier function, and so on. So from these 6 block states, I can construct these 6 Wannier functions, and these 6 Wannier functions span exactly the same Hilbert space as these 6 block states. Now there's a slight dirty secret here, which is this Wannier function in the supercell representation actually appears here, and then it's 0 for a while, and then it becomes non-zero, and then it's 0 for a while. So it has periodic images in the superlattice. So that's, and then if you let the k-point mesh become small, they get further and further apart, and it's not a problem. But I mention it because of something that is going to come back in a few moments. Okay, so here's the band structure of silicon. There are 4 occupied valence bands. Here it looks like there are 3, but along a branch it's degenerate. And what we want to do is construct 4 Wannier functions per unit cell, which span exactly the same subspace of the Hilbert space as is spanned by these block functions. And so we go through this procedure. We have our 4 occupied states. I'll tell you in a moment how we make a first guess of these unitary functions, and we go through this procedure, and we minimize with respect to the unitary matrices, and we get, so again, this is basically just saying the same thing. Again, I've dropped the notation. I'm just trying to get my notation. So when you don't see the lattice index r in the Wannier function, by definition, that's the home unit cell. I forgot to say that. So you basically just need to calculate find the Wannier functions in the home unit cell, and then you know the other ones by translational invariance. Oh, it was here. And so you're basically minimizing this quantity for the 4 Wannier functions in the home unit cell, and then you end up getting some cute object that looks like this. This is the Wannier function that you compute in silicon. What I'm showing here, the red is an isosurface of the positive amplitude of the wave function, and the blue is an isosurface. Oh, this is not silicon. This has to be gallium arsenide because it's asymmetric. So I'll come to it in a moment. And then the center of charge of the Wannier function is an important quantity to keep your eye on. It's like the center of mass of a mass distribution. So that's where if I want to think of the electron as localized at a point of space, I would think of it as localized at the Wannier center. But then its spread around the Wannier center is described by this omega. Don't confuse this omega with Berry curvature. It's not Berry curvature. It's a spread of the Wannier functions. And so if you do this for silicon, here's the picture you get for silicon, so it looks symmetric. And it sits in the middle of the bond. So the basic chemistry of silicon is that it's a covalent system, and the occupied space is basically made out of bond orbitals. You take an sp3 and an sp3, and you make a sigma bond orbital, and you occupy those sigma bond orbitals, and this is the sigma bond orbital that you get for silicon. Now, I'm cheating a little bit with this picture because this Wannier function has a little bit of amplitude on some neighboring sites, and I chose the isosurfaces such that they don't show up at all. But the Wannier function actually does have some amplitude on neighboring sites and then decays exponentially as I go away. And here's what you get for gallium arsenide. Oh, let me come back and say something that I wanted to say about initializing this procedure. So you may ask whether it's possible to do this at all, whether it's possible to make these unitary choices in such a way that these block functions are smooth. And the reason that it's a serious issue is that when you come to some degeneracy, like there's a degeneracy here and there's a degeneracy here, let's talk about this one. If you follow this particular branch along the Cartesian x direction, well, let's take this one because yeah, that's right, this one is non-degenerate. So if I follow this and take the limit that k goes to 0, I get a certain Hamiltonian eigenstate. If I do it instead from the y direction or the z direction, I get a different eigenstate of the threefold degenerate state at gamma, and therefore, if I look at the Hamiltonian eigenstates, there's a singularity at gamma, there's a discontinuity that I have to erase. And so what I have to do is I have to choose my unitary matrices in such a way as to erase that singularity. And there's a procedure for this that I won't go into very, very carefully. What you do is you choose some trial function according to the chemistry that you think you know. In this case, you think that the Wannier function is going to be on this sigma orbital. You put some trial wave function here. It can just be a simple S-like Gaussian or something. You take that trial function, and at some wave vector k, you construct the projection operator out of the 4 block states at that wave vector k. You multiply that projection operator onto this trial state and renormalize it so it has unit norm. And that's going to be your first guess at the trial sigma tilde. And if you do that throughout the Brillouin zone, even though you're passing through this region where the block states have a singularity, the resulting psi tildes from that projection operator are completely smooth. And using that, you can get a first guess at the Wannier functions, which is actually often quite a good guess. And so this is what's called the projection procedure, which gives you a starting point for the iteration as implemented in the Wannier 90 code that I mentioned. Okay, here's what you get if you do the same thing for gallium arsenide. It's what I showed before, obviously. It's similar to silicon, but there's an asymmetry because arsenic is more electronegative than gallium, and so you get this asymmetry where you're basically building this out of sp3 orbitals, and so this negative lobe over here is the little negative piece of the sp3 orbital. This is sort of a cute picture of what you get for the P-like Wannier functions on oxygen in strontium titanate, which is a well-known perovskite material. And I told you that the Wannier functions sometimes have some amplitude on the neighboring sites. In this case, the p orbitals in the oxygen hybridize with the titanium d orbitals, which are nominally unoccupied, but there's some hybridization. And so the oxygen p orbitals acquire some titanium d orbitals, and they make so this is a pz oxygen orbital, and this is a dz squared titanium orbital, and this one also. They hybridize together to make a Wannier function that looks like that. And this is a px, so this is like the pi-like version, and this is a sigma-like version. So kind of cute, in my opinion. Question, yeah.
Thanks. So like you not only minimize the spread, right? You also minimize some, like the difference to the eigenstates, or do you minimize the difference to the block states you had before?
No, I've seen papers where people have implemented something where you minimize the energy spread with some weight, at the same time you minimize the spatial state with some weight, but that's a very much minority approach. The standard approach is you decide on an occupied set of bands that you're interested in Wannierizing. They have some energy spread, and when you construct the Wannier functions, you don't care. I mean, they're not eigenstates anymore, but they're linear combinations of these things. So the energy, there's a spread in energy, and you just don't care about it. You don't care how delocalized they are in energy, but they are all living in the subspace spanned by the block states, right? So they all live in this energy window, so to speak. And that's all you care about. You don't care about localizing them in energy anymore. They're not energy eigenstates. But the spread in energy is no bigger than the spread of the band group that you built them out of.
Okay. So like you don't fit them to the ab initio bands at all, but like...
Well, you use the initial bands because you actually don't use the energies of the initial bands. The only thing you use is the block eigenstates themselves. And you think about the subspace of the Hilbert space that is spanned by the block eigenstates. So at this point, you've forgotten about the energies. You just are thinking about the set of block eigenstates, the band projector in the language that some people use. And within that subspace, you want to construct a new basis that spans exactly the same subspace but is localized. So this procedure ignores the energy. Once you have the block eigenstates, you ignore their energies and only use the wave functions themselves.
Okay, thank you.
There's another question up front, or if you'd like, I can just repeat the question.
Yeah, my question is, what goes wrong when you, like technically speaking, when you not do it with a full set of bands? Like you're saying that, so imagine I pick up like bands that, yeah,
I'll talk about that.
Okay.
Okay, so the procedure that I'm talking about here is typically applied to insulators. So maybe I should have said at the outset, and it'll become clear as I go along. There are two contexts in which people do this. One context is you have some set of occupied bands in an insulator, and you're going to Wannierize those bands. And you're going to end up with a number of Wannier functions which is equal to the number of occupied states, and that has the same, spans the same space as the occupied subset. And this is very useful for topology and for things like electric polarization, orbital magnetization, because it describes the occupied subspace, but only works in an insulator. There's another procedure, which is what I call, we'll call disentangling, where what you would like to do is, for a metal, for example, you Wannierize all the occupied states and some of the unoccupied states in order to have a basis in which to describe the occupied part of the manifold accurately. And so you use that to generate a tight binding like Hamiltonian to use as a basis, but it's no longer true that the set of Wannier functions corresponds to any any occupied manifold in the same sense as my first example, where I'm looking at an occupied manifold of an insulator. So I'll talk about that in a little while. So let's hold off on that. Yeah, Jen.
So have you ever run into a situation where you maybe, if you're trying to minimize the spread, you end up in a local minimum, but maybe it's not close?
Yeah. Yes, it is a problem that the procedure for doing this minimization is one that can suffer from local minima. And if you, for example, choose your unitary matrices randomly on the first iteration and then just try to minimize, you will often get stuck in situations where you have you're stuck in a crazy local minimum where the spread is much too large. So the projection procedure that I mentioned earlier almost always allows you to avoid that. You have to have some chemical intuition, however, about, it's this, for example, on this tin atom, there is an occupied non-bonding orbital that so you have to have some intuition. You might have to try different things, but when you try the right thing, then you'll find a set of quite localized Wannier functions and you declare success. Okay, so let me so I'm glad we had some questions there because now I'm doing kind of a segue into the electric polarization part of the problem. So suppose I have some crystal and I'm sort of drawing a toy model here where the blue plus signs are the positively charged point nuclei and the electrons are distributed by quantum mechanics into diffuse charge clouds that I'm kind of illustrating like so. And so I told you that I can do a Wannier construction, and from the Wannier construction, I can find the center of charge of the Wannier function, and now I can draw a picture where I ignore the actual diffuse charge cloud, and I copy the locations of the positive point nuclei, and now I have negative point electrons in a spinless system like silicon. I would actually have -2 charge at each electron position because of the spin degeneracy. And so I can think of a fictitious physics in which I have point-like nuclei and point-like electrons attached to the unit cell in a periodic fashion like this. And from this picture, I can, so here I do it for some case where I have a nucleus with charge 4, and then there's spin degeneracy, so each of these two Wannier functions per unit cell have charge -2. And of course, this is a centrosymmetric picture, and so in this case, the polarization in some sense is 0. But in general, if I have lower symmetry, I will see the negative charges distort with respect to the positive charges, and that will generate some polarization. And it turns out that the polarization that you deduce from this picture of mapped point charges that are obtained through the Wannierization from the first principles calculation corresponds exactly to how we calculate polarization in a first principles calculation. And it's related to Berry phases in a way which I have to discuss. It doesn't sound like it's related to Berry phases, but it is. So let me, when I'm about halfway through, okay, maybe I'll try to accelerate a little bit, but some of this will go more quickly. Okay, so suppose you have a polarized crystal. In a textbook, it's usually built out of little polarized entities with vacuum in between, but I told you that real materials are not like that, and in fact, what real materials look like, here's a picture that Nicola Marzari generated for us once a long time ago of an isosurface of charge density in some lead titanate crystal. Obviously, there's no region of space where the charge density goes to 0, so the charge density is distributed. And so the first thought is let's calculate the dipole moment per unit volume, which is the polarization, by just constructing some unit cell and calculating its dipole moment. Now you see I've made these charge clouds a little bit asymmetric, so in this case the dipole moment is not not zero, but close to zero. But if I put the unit cell here, obviously the dipole moment is strongly in the up direction. And if I put the unit cell here, it's strongly in the down direction. And if I choose all possible positions of the unit cell and average over all of them, I get identically zero. And so it turns out that inspecting the charge density, in fact, the correct statement is that a perfect knowledge of the charge density in the unit cell is not enough to tell you the polarization. You have to do something else that somehow depends upon the phases of the block wave functions or else the locations of the real space Wannier functions. So again, we have these cell periodic block Wannier functions, block functions, and we're going to use those for the following reason. I said before that matrix elements are the position operator. So to calculate the dipole moment, you want to take the expectation value of the position operator. That's what you would do in a molecule. But you can't do it between block states because it's ill-defined. So there are two tricks. The first trick is, as I think Dima mentioned, you have a kind of a correspondence in quantum mechanics that says that if momentum is the gradient with respect to position, the position should be gradient with respect to momentum, which is wave vector, effectively, in the crystal case. So I can replace this R by a gradient with respect to wave vector, which has the same units, and it's plausible. But it turns out that this thing, the derivative of the block function, is still ill-defined because the block function has this phase dependence in such a way that when I take the wave vector derivative, I'm also taking a derivative of the boundary condition, and so this turns out also to be ill-defined. It blows up at large x when x gets large. But what doesn't blow up, what is perfectly well-defined, is if I replace the block functions by the cell periodic block functions. These all live in the same simple periodic boundary conditions, and there's no problem with taking wave vector derivatives of those. So in my view, you have to play some tricks in order to tame this position operator. The Blount approach was one set of tricks that was used. The set of tricks that's being used here, and which I think is commonly adopted in the modern view, is a slightly different set of tricks. You make this substitution and this use the cell periodic block functions, and then the problems go away. Can be carefully treated. And so the result of this is that you can derive an expression for the polarization by looking at an expression that was derived by Resta for the change in polarization as you make some adiabatic change to the system. That's this formula. And if you analyze, if you use a linear response theory to write down what the first order change of the polarization is as you make some adiabatic change, that thing actually involves a current flow and is perfectly well defined. And then you evaluate the integral and rewrite it in terms of the initial and final configurations. Then the polarization at the final configuration takes this form. So I'm obviously not deriving this for you. That would be another talk. But the point is that this now looks like a Berry connection. It's UNK, gradient with respect to K of UNK. That's the Berry connection in a particular Cartesian direction. And you integrate that over the Brillouin zone and multiply by some constants, and that tells you what the electric polarization is. And so this is the, oh gosh, it's hard to believe that was 30 years ago. This is what's called the Berry phase formula, or the modern theory of polarization. So I want to explain a little bit about how this is related to Wannier functions, and so that's what the next few slides will be pointing towards. So let's do this in one dimension to make things simple. So this is basically the Berry phase of the block band represented in terms of the cell periodic block functions. This is the Berry connection. I integrated over the closed loop, which is the one-dimensional Brillouin zone, and I'm telling you that that Berry phase divided by 2 pi gives me the polarization. So again, I'm writing this heuristic connection, and I'm writing that this is the Berry phase, and the polarization is just the Berry phase. So I wrote this as a closed loop integral, and again, that's because while in textbooks we think of the band as written along a segment in reciprocal space. It's actually an extended zone scheme where these states are duplicate labeled of those states, and so I can perhaps more intuitively think of this one-dimensional Brillouin zone as a closed loop, and I could plot the band energy on the surface of this cylinder as a way of, I mean, you can't do this in textbooks very easily, but this is the way that I now think about an energy band of a one-dimensional crystal. And because it's a closed loop, then we have a closed loop integral, and that allows you to define a Berry phase. So we have the Berry phase of the band, or the Zach phase. Someone was asking about terminology. This is the Zach phase. I don't know why it keeps doing that. And that's very strange. Okay. So how is this related to the center of Wannier functions? And I think we saw something like this in Dima's talk also, or one of the talks. So the Wannier function is basically the Fourier transform of the block functions. And the one in the home unit cell is really just the integral because it's the one that's as localized as possible. It's the integral over the whole Brillouin zone of the block function. And I can write that as the phase factor times the cell periodic function. Then if I multiply by position, I can replace the position operator by the gradient with respect to k acting on the phase factor but not acting on u. And then I do an integration by parts, and then the gradient of k acts on the u but not the phase factor. And then when I put the other omega naught in the bra and close the sandwich, I get this expression. So this is the center of charge of the Wannier function, and this is the Berry phase of the band. And so they're one and the same thing. That's the message. They're one and the same thing. So for example, here I've got this one-dimensional crystal. These are the positive nuclei. The negative electrons are initially spread out as a charge cloud, but I calculate the Wannier centers. Of course, the Wannier centers form a lattice. The center of charge of the Wannier function is this thing. It's written in terms of the Berry phase, but the center of charge of the Wannier function is therefore just the Berry phase times the lattice vector over 2 pi. So in other words, when the Berry phase is 0, it means that the Wannier center is sitting on top of the atom. As the Berry phase changes from 0 to 2 pi, as I make some adiabatic change to the crystal that changes the Hamiltonian, if I do that, and if the Berry phase evolves from 0 to 2 pi, the center of charge of the Wannier function shifts from the left edge of the unit cell to the right edge of the unit cell. And so the Berry phase is telling me how far is the charge center displaced from the nuclear center, which is nothing other than the polarization. Okay, so as I said, there's a lattice of Wannier functions. And again, here's the polarization written in terms of the Berry phase, or more generally, the three-dimensional Berry potential, Berry connection. There's a subtlety here, which is the polarization has a sort of a is ill-defined up to a quantum, because I can think of this unit and calculate its polarization, or I can think of this unit and calculate its polarization, and the two polarizations differ by a quantum, which is just the quantum of charge times the lattice vector divided by cell volume for the polarization. So that's a subtlety that comes into the theory that I don't want to expand on here, but it's very important for some applications of the theory of polarization. So now okay, let me take the question, and then I'll just finish this, and then I'll move on to other things.
So the theory doesn't know where the atoms sit? Like, it only knows about electrons, right?
Well, so...
And the atoms are assumed to sit at 0, or...?
So I cheated. So this is the formula for the electronic contribution to the polarization.
Okay.
To that, I have to add the nuclear nuclear contribution to the polarization, and that gives me the total polarization. And so what I really do is, if I go back to this picture, I hope I don't have to go back too far, where I have the, oh gosh, I guess I do have to go too far. Well, I'm trying to go back to this one, right? So in the end, what I get is a set of Wannier center positions, which corresponds, and so if I sum up the contribution of those to the dipole moment, that corresponds to the electronic piece. But then I also have to add the nuclear piece, and because the crystal as a whole is neutral, at the end of the day, I get something well-defined. So for example, the purely electronic piece depends on where I choose my origin, but that dependence upon choice of origin goes away when I include the positive ionic charges, and then I get something that's well-defined. So thanks for the question.
Okay, thanks, Sue.
Yeah, there's a question up in the front, too.
Thanks, sir. I just have one quick question. So, as you showed very nicely, the classical polarization picture of charge distribution depends very much on the unit cell, right? It's ill-defined. Is there an easy way to see why this problem is solved with this? Because, of course, the UNKs and the Brion zone choice still depends on your choice of zone, right? So if you choose a different zone, you get different UNKs. Is there an easy way to see why this is going on?
Well, that basically corresponds to what I said, that if you change your choice of origin, which is equivalent to changing your choice of unit cell location, then the electronic contribution to the polarization does change. But actually, then the location of the positive charges in the unit cell is different in equal and opposite way. And when you add the two things together, it's invariant.
Okay. All right.
There's another question.
In the starting expression for the Wannier function, you had some u also. But when you're writing this expression, you remove the u.
You mean the uppercase U, the unitary matrix?
Yeah, the unitary matrix.
Yeah. So the unitary matrix is the thing that takes you from, how should I put this? So if you had a molecule, these would be the Hamiltonian eigenstates, and there would be an X operator in the middle, and these would be the Wannier states, and there would be an X operator in the middle. And those two things are equal because I'm taking the total expectation value of some one particle operator in a set of states, and the set of states that I'm using here and the set of states that I'm using here are exactly span the same space, and so forth. I must get the same answer when I calculate this matrix element. The trick here is that on the right-hand side we have a block crystal, and so we've done the unitary transformation that we've done is not as transparent as it was in the molecular case. It's hidden in the transformation from these cell-periodic block functions U to the Wannier functions N. But the principle is the same. This is basically an X matrix element, and I'm basically taking the expectation value of the position operator in the block space here and in the localized space here, and because it's a unitary transformation, the answer must be the same. That's the best I can tell you at this level.
Thank you.
Okay, let me make this comment because I showed a picture like this yesterday, and I just want to repeat it. And I think it will be a lot clearer what I was trying to say yesterday now that I have done this introduction. So I talked about the case of a two-dimensional quantum anomalous Hall insulator, and I said that if you look at a particular kx in the Brillouin zone and compute the Berry phase along the y direction, that's phi y as a function of kx, it varies like this in the case of a Chern insulator. It has it migrates by a value of 2 pi as I go across the Brillouin zone. And now what I'm telling you is that the position of what I'm telling you is that the Berry phase in the y direction corresponds to the center of charge of the Wannier function in the y direction. And so if I look at those one-dimensional Wannier functions as I apply an external electric field that drives wave packets from the left side to the right side of the Brillouin zone in kx. So this is, again, one of these hybrid pictures where I'm drawing kx in this direction, well, and either real space y or Berry phase in the vertical direction. So it's a little hard to wrap your mind around that. But this is real space y and reciprocal space kx. You drive an electric field. All these Wannier center positions shift in the y direction and generate a current in the y direction. and that current is the anomalous Hall conductivity. And it's quantized in the quantum anomalous Hall case because, as I said yesterday, actually the Berry phase has to evolve by 2 pi as I go across the Brillouin zone, and so that gives you the quantization. I wanted to mention about topological obstruction because this is a workshop about topology. It turns out that, in general, I told you that you can do this even if there's some singularity in the block states at a particular degeneracy. But that's not a problem. What can be a problem is if the occupied space as a whole is topological. And in that case, it may be impossible to choose unitary functions in such a way as to make exponentially localized Wannier functions. And the standard example of this is the two-dimensional quantum anomalous Hall insulator. So for the quantum anomalous Hall insulator, you do have an occupied manifold separated by a gap, but it is not possible to make exponentially localized Wannier functions for that manifold. I thought I was already out of time. Good. And one way of seeing that is that because I integrate the Berry curvature over the Brillouin zone, I get 2 pi. So that says that if I choose a gauge, if I choose a gauge that makes the Berry connection smooth and continuous in the interior, then the Berry curvature is well defined everywhere inside, and it has to integrate up to 2 pi. And then Stokes' theorem tells you that when you do a boundary integral around the Brillouin zone, you get 2 pi. But that's inconsistent with choosing periodic boundary conditions in reciprocal space for the block functions, because if you do that, the block functions at the top and bottom and left and right are identified, and when you do the integral around the boundary, you get 0. So that's one way of thinking about it. The other way is if you insist that the boundary Berry phase is 0, and then you choose the gauge inside, there has to be a vortex, a singularity in the gauge somewhere in the interior. And so in either case, if you try to, in this case, you could go ahead and try to do a Fourier transform and construct Wannier functions, but since you have a singularity in k-space, that's a very localized thing in k-space, it makes the Wannier functions have a very poor localization, just power law tails, like 1 over x. And so then you can't do anything with them. So that's basically a hand-waving demonstration that in the presence of a topological index, you can have a topological obstruction to the construction of Wannier functions. And that's what happens in the quantum anomalous Hall case. In other cases, there's some additional discussion of symmetry. For example, the strong topological insulators are defined in the context of the presence of time reversal symmetry. And there the correct statement is you cannot make a Wannier representation where every Wannier function has a time reversed partner. So pairs of Wannier functions that are Kramer's degenerate. That's what we would normally do. You cannot do that. You can actually choose Wannier functions that violate. So sort of in the gauge, you violate time reversal symmetry. But you cannot construct a set of Wannier functions that has time reversal symmetry. And the same thing for example, crystalline topological insulators. If you have some particular symmetry like a mirror, and if you have a mirror topological insulator, then you can't construct Wannier functions that respect the mirror symmetry. Okay, so now I want to come to the point that I talked about before, which is in answer to a question, what happens if what you really want to do is describe not just the occupied space, but some additional bands as well. And so, yeah. 7 minutes, good. I think I can do that. So this is a band structure of bismuth selenide, which is one of the well-known topological insulators. There's some deeper core states here that we're not so interested in. There's a trivial gap here between them. And these are essentially the p orbitals on the selenium and the bismuth, which are the relevant ones. And then up here are some higher orbitals, like some higher sp orbitals and of higher index and so on. And so what you would really like to do is to look at this manifold of states. So there's no well, there actually is a small gap, but you'd like to describe the entire set of 30 bands, which includes these 18 bands and these 12 bands, which makes an entire set that corresponds to all the p orbitals on all the 5 atoms in the unit cell. And so now it's not going to correspond only to the occupied subspace, but to some larger subspace. And without going into much detail, just the procedure is more or less you identify an inner window, and the idea is that I want my Wannier representation to reproduce the full calculation inside that inner window. And in doing that, I'm going to mix in some states that come from the outer window. So there may be some region here where I have to mix in some higher states in order to do that. And so again, you use projection to do an initial starting guess. And there's some details to this. I can give people pointers to the literature if you're interested in how this is done. This is what we call disentangling, and you have to be careful here because this is not entangling in the sense of quantum entanglement. It's like you have a bunch of spaghetti, and from the spaghetti you want to disentangle the band that you're interested in. That's the sense in which this word was used. And so if you do this for the case of bismuth selenide, you can get a very nice description, which are the red bands, which is the Wannier representation, which falls right on top of the first principles calculation, except in some regions that are far enough above the Fermi energy region that you don't care about it. Essentially, what you do then, and what you do when you do this, is you start with a first principles calculation on some mesh, relatively coarse mesh, let's say 6 by 6 by 6 K points in the Brillouin zone, and then from those. You do the Wannier construction, and you record matrix elements at the Hamiltonian between the Wannier function in the home unit cell and all of the other 6 cubed cells in my supercell. Actually, this is where the point comes in that I said before, that the Wannier function in the home unit cell in the supercell construction actually has an image over one superlattice vector away. And you don't want to include interactions with that. So then you do a cutoff up to some radius. You save all the Hamiltonian matrix elements up to that radius. You also save X, Y, and Z matrix elements if you eventually want to compute Berry connections and Berry curvatures. And this gives you a kind of a generalized tight binding model. And then from that tight binding model, you can go and compute properties. I'll get to in just a second. And so, for example, this is for this is for BCC iron from one of the early papers. In this region of the band structure, the construction was actually only done on the coarse mesh, but then if you compare the first principles calculation with the Wannier calculation, they fall on top of each other almost perfectly, even between the mesh points, because you've used the information in the block functions imported into the Wannier functions to generate this first principles-based tight binding-like model that gives you an almost perfect description of the band structure at a very fine case-space scale. So, question?
We typically estimate the goodness of the vanillization in
I think the mic was not turned on. Well, I'll repeat the question.
So we estimate how good the vanillization is. Yeah, thank you. So we estimate the goodness of the vanillization as how the Wannier bands fit the DFT bands, right?
Yes.
So how good is this measure of goodness, let's say? So if I have some set of Wannier bands that reproduces the bulk bands, just the eigenvalues, is this also a good reproduction of like the physics behind the Hamiltonian?
Yeah, I think, it's not guaranteed, but the construction is such that the information, okay, so, what some people will do is they'll take a first principles band structure. The only information they use is the energy versus K of the bands, and from that they try to construct an effective tight binding model. This is much, much better than that because actually you have all the information, and in some sense you have used the information about the chemical character and actually the detailed internal structure of those block functions. You build them into the Wannier functions, you build them into the matrix elements that you calculate. And so you expect it to be good in all respects, not just in respect to getting the energies right.
But is there any way we can actually check this, like any measure of?
Well, you can calculate, some, expectation value of the spin density at some wave vector from first principles and from the Wannier interpolation, and you check that you get the same answer and so on. So, yeah. Okay, I think I'd better go on because now it's not just taking pictures, but they want me to finish. And so what am I going to do about this? I think I don't have time to describe this properly, so I'm going to scoot ahead and tell you this. And what I skipped over is some physical motivation about why and how this works. But let me go here, and then I only have 2 or 3 more slides after this. So in one dimension, there's a Berry connection and a Berry phase. In 2 dimensions, there's no real, well, of course, there's Berry phases in the x and y direction as a function of wave vector in the other direction, but there's no mathematical object which is like that in 2 dimensions. Instead, in 2 dimensions, there's a Chern number. The dimensions kind of alternate. So in 3 dimensions, it turns out that there's another object which is a little bit like polarization, and it's called the axion angle theta, and here's the formula for it. So in this formula, A is the Berry connection in Cartesian direction A, but this has to be in a multi-band system. So for example, our silicon system had 4 bands, and this n runs over 4. And so each of these is a 4x4 matrix, and these are 4x4 matrix multiplications. And then you trace this over the occupied space, and that's the antisymmetric tensor, and you integrate it over the 3-dimensional Brillouin zone. And it turns out that this object is something that's well known from gauge field theory. This is the Chern-Simons 3 form, and this is what's known as the axion angle. And the reason that this is like polarization, it's like the Berry phase in 1 dimension, is it turns out that this is well-defined modulo 2 pi with respect to gauge changes of the choice of the block functions. And so it plays a similar role. And what is its physical interpretation? The physical interpretation is it gives rise to a diagonal contribution to the magnetoelectric coupling alpha. So the magnetoelectric coupling tells you that if you apply an electric field in a certain direction, you get a magnetization in that direction, or conversely, if you apply a magnetic field, you get an electric polarization in that direction. So it gives you a contribution to the isotropic magnetoelectric coupling, which is actually quite small in normal materials, but can be much larger in topological materials. And so what I was going to do, maybe I'll just flip forward because, as I said, I think it's only 1 or 2 slides. Let me go over this. That really is, I see, yeah, okay. So just to finish this, I wanted to discuss what happens to Maxwell's equations when you have this kind of isotropic magnetoelectric coupling. And what I've done here is to write down Maxwell's equations in terms of E and B in the presence of the bound charge, bound current, and polarization current. Of course, one way of dealing with this is you introduce H and D fields, and then it simplifies. But another way of dealing with it is to separate out the part of this that comes from the magnetic field or the electric field, and the part that would otherwise be there. And if I do that, I define these rho tilde, J tilde, and B tildes in terms of P naught and M naught, which are the parts that would be there in the absence of the fields. And then you have these extra contributions, and these extra contributions correspond to what's known as axion electrodynamics. This is partly of interest in elementary particle theory because there's some thought that there may be an axion background of the fundamental background equations of quantum mechanics in our universe. But in the material system, where this would be coming from is from this magnetoelectric coupling that is introduced via the theta coupling. And so the full picture is that you have these extra terms. These extra terms only depend on either spatial or time derivatives of this axion coupling, the magnetoelectric coupling. So at the end, it doesn't do anything really in the interior of a crystal, but at the boundary of a crystal, you have a gradient, or if there's a time dependence, you can get an effect. And so if you put these together with the equations of motion of the particles, and these are the equations of motions of the fields, this is one way of looking at the big picture of all of the equations of motion for particles and fields in a crystal in the case of a crystal of very low symmetry where you have magnetoelectric coupling. Okay, so obviously I did a very short version of this last point, but that's okay. I think it's important just to be clear as we go along. And if you're interested in this, I can point you to references about it. So sorry to be going over time, and thanks for your interest.